So again, the goal is questions from the review. What I'm going to do is if you ask me a question, I'm just going to change the numbers. I'll change the acceleration. I'll change the mass. And I'll walk through how I would do it with those numbers. Again, for all of you, you can write this down if you want to, or you can just watch. And if you stick around to the end, 4-ish or so, I'll print this up for you when we're done. If you can't stick around till the end, I will also put this on the website somewhere. You can get it tonight by about 7 p.m., I hope. Questions from the review. Any questions from the review? Any questions from the homework? Any questions from anything but focusing or primarily talking about the unit review? Any of these that you want me to go over? Love to. I like number 10. I like number 10. I like number 10. I think number 9 and number 10 go together. So, Anthony, I'm going to do number 9 followed by number 10 because they're kind of opposite sides of the same coin. Okay. You guys have done friction already, right? You know that friction equals mu times the normal force. Okay, you've learned that. Good. And you probably talked about how technically there's 2 different types of friction. And again, I don't emphasize this, but it's true. There's 2 different types of friction. There's static friction, which is why this question is talking about mu with a little s for static because it's not moving yet. And then there's kinetic friction once it starts to move. This explains why once you get something sliding, it's easier to keep it sliding. I am not going to test you on that, but the nerd within me does have to at least mention it every time because it's technically I'm teaching you sloppy and I don't like doing that. So this one here, which I also like, key idea, question or done? Can you put it in block H for me, please? Thanks, kiddo. And any other missing assignments you want to put them on top, that'd be great. The key concept, the key phrase, the key idea is that there. First of all, how would I start this? Really? How would I start this? I would do some kind of a free body diagram. You know what? Since they gave me a picture, I guess I'll label the picture. What are the forces acting on this box? Get the obvious one. Is the box sinking to the ground like quicksand? Is it lifting into the air like Superman? So there must be same size force. I'll draw an arrow the same length. And we call that, and you guys have learned this already, right? The normal force. The ground does actually push up. It's a Newton's third law. Forces come in pairs, reactive force. What else? Okay, we call this the applied force. And it looks like it's 100. What else? Well, what did I, friction. And what did I underline, Jake? The fact that it just starts to move, I think what they're trying to say is friction has just finished tying the applied force. It has just started to move. In other words, normally I'd go, who's winning? Winner minus loser equals MA. I think the fact that it just starts to move, what it's saying is friction equals the applied force. Now, I said I was going to make up different questions, so just let's do that. If you're doing this on that question, now all the numbers are going to be different. You want to stop writing. I'm going to say I'm going to make the box 30 kilograms. I'm going to have it pulled with 200 newtons and 200 newtons. So let's cross that out, make it 200 newtons. There, it's a brand new question. Okay? Do you see why I was able to do that? Normally it's winner minus loser equals MA, but the idea we're saying is if it just starts to move, it hasn't quite started accelerating yet. A is 0. And that's why it wrote in brackets, i.e. the maximum value of static friction has just been overcome with a force of 200 newtons. Probably it really means that friction is 199.9999999 newtons, but it's 200. Okay. Friction is what times what? Mu times the normal force. You guys don't have me. If you want to see me snap, say friction is mu mg. It is not mu mg. Friction is always mu times the normal force. And F applied in this question that I've just made up is 200. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What force is the same size as the normal force in my free body diagram? Mg. And again, you've never ever heard me say normal force equals mg. You've always heard me do that stupid little look, 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 look. I'm trying to emphasize, I am never saying that normal force and gravity are the same thing. I'm saying in this case, because of Newton's first law, they have to be the same magnitude, which is important in Physics 12. What am I trying to find? How would I get the mu by itself? So in this case, mu is going to be 200 divided by, I changed the mass, I made it 30 and 9.8, and hopefully I get an answer that isn't ridiculous. By the way, since I'm making up numbers, some of these answers might just be stupid answers, but such is life. 200 divided by 30 times 9.8. Yeah, I get a pretty sticky coefficient. That's about tires on rubber. This would not be that pleasant to slide. You'd have to be pulling pretty hard, but 0.68. Okay, which is not that answer because I made up different numbers. Now let's answer your question. Number 10 is very, very similar, except in number 10, hey, we're moving. Okay. Oh. Did I say I like this question, I like this question, I like this question? Because I should have. Okay. Let's make a new question. How about 7 kilograms? How about 31 newtons? I'm just making up numbers. Oh, how about an acceleration of 1.8 meters per second squared? That might have been bad. I probably should have made it go faster because I'm pulling harder. Well, whatever. Suggestions, Anthony? In fact, I'm fairly certain, I know there's a question very similar to this where I ask you part A to draw the free body diagram. And because I think the question is fairly similar to this one here, I'm not going to label the forces on the picture. I'm going to draw the free body diagram just to show you what your answer might look like. Free body diagram means representing the mass with a dot. What are the forces, Anthony? Get the obvious one. Get the obvious one. Thank you. And the reason I'm so fussy on getting that one first is you can't assume there's a normal force there until you convince me that gravity's pulling it down. Because then I'm reasoning, is it sinking into the ground like quicksand? And your answer is it lifting into the air like Superman? And your answer is? Which tells me that there must be, Newton's first says the vertical forces must be balanced. And that's why we so often just ignore those in our equations. What else? Must be an applied force. 31 newtons, but an applied force. What else? Is there friction or not? Which way? And why did I draw friction shorter than applied versus up here? You'll notice I tried to draw friction the same length as applied. What's the difference? The fact that there's an unbalanced acceleration in the question, 1.8, tells me, you know what? It must be shorter. Now, I have a feeling it's barely shorter, and I've exaggerated it, but I try to exaggerate bigger and smaller in my free body diagram to really emphasize who's winning. Who is winning? That means anything that ends up pointing to the right is going to be winner. Anything that ends up pointing to the left is going to be loser, which means and that equals the net force, and the net force is always MA. This year. So far, so good? Okay. They're asking me to find mu. I guess I better say friction is what times what? That's going to give me a mu in here. So I'm going to say the applied force minus mu times the normal force equals MA. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. So in the interests of time, I would normally rewrite this, but I'm trying to fit this all on one page, so I'm going to do that right there, if that's okay. What am I trying to find? What's mu? I don't know. What's mu with you? Yeah, I'm trying to find mu, right? How would I get the mu by itself? I'll be honest, there's several ways. One way, which I would choose not to do because I hate negatives, one way would be to go minus F applied, divide by negative mg. Perfectly acceptable. Have I mentioned I hate negatives? You know what I'm going to do, because I can do this in my head intuitively. I'm going to plus that to that side at the same time minus that there, because I don't like a negative in front of the mu. I can live with negative in front of stuff that I'm not trying to get by itself. I just hate negatives in front of what I'm trying to get by itself. If I'm stuck with them, I'll use them. But I think this is the same equation. You okay with that, Chris? Mm-hmm. Yep. But I would argue that looks much nicer to get the mu by itself. In fact, how would I get the mu by itself? Divide what? Divide by mg. Yeah, no dividing, but because otherwise sometimes I see kids divide by mu to get the mu by itself. No, you don't want it on the bottom. Worst place to find anything is on the bottom. I'm doing all my work to get it onto the top. Yeah, I think I can say this. Mu is going to be the applied minus ma divided by mg. Okay? By the way, this is some of the stuff we would start to ask in Physics 12. We would say, okay, this equation apparently describes how you can figure out what the coefficient of friction is. What would happen if you had to pull harder? What if the applied force was bigger to get the same acceleration? I guess that means mu is bigger. Oh, that must mean the floor is stickier. Which seems obvious. If I have to pull harder, the floor is stickier. But there's the proof. Okay? Or you could ask in Physics 12, we would say a question like, oh, what if I don't need to accelerate as fast? I could probably not have to pull as hard with the same mu. You start looking at, that's why I'm also teaching you to get the letters by themselves before, and I think Mr. Kamosi is as well, before plugging in the numbers, because those of you that take Physics 12, we really start to then say, hey, let's see if we can get one equation and answer a bunch of stuff generically using our reason. Anyways, if I crunch the numbers, the answer is not going to be 0.2. Mu is going to be, what did I say the applied was? 31 minus 7 times 1.8, all divided by 7 times 9.8. Is that okay, Anthony, as an explanation? Does that work for what you were trying to do on the real number 10? It's going to be 31 minus 7 times 1.8, close bracket, divided by bracket 7 times 9.8. I think it's going to be pretty low. Yeah, 0.267. Is that right? Yeah? So 0.268. 0.268. Really wet pavement, the kind of wet pavement that you can almost slide in your shoes on, but not quite. You sometimes notice it on a hot summer day. That's about a point. That's about a 0.3. So you could walk on it, but you could also slip on it if you weren't careful. Cars would not be too comfy driving on this. They would skid fairly often if they were trying to go around a corner or if they were braking. Is that okay? Next. Yep. 4. This is the same as number 9. I'm just going to, I'll get you started, but it is, and I'll change the numbers, and I'll try and convince you, okay? And one of the things I'm trying to teach you, Darian, is categorizing questions and recognizing when the physics is the same. Let me make this a bit smaller. First of all, changing the numbers. Hey, how about making it 370 newtons? And let's make it a 43 kilogram box. There, now it's a new question, so that's not going to be the answer anymore. Ready, Darian? What's this a job for? Yeah, and if you didn't draw a free body diagram, shame on you. Free body diagrams take 1 second or so, but they are so invaluable. So you ready? There's the box. What are the forces acting on it? Get the obvious one. Okay? students that aren't mine, I always start with gravity first. I always like to get one force on there that I know is there. The only time you have to be careful is when you're in outer space. Then the obvious one isn't the obvious one anymore. So but almost always get the obvious one. What else, Darian? Because it's not sinking into the ground or lifting up. What else? There's an applied force. Yes, you agree with me? What else? Okay, tell me when to stop drawing. How do you know that I want that arrow to be the same as the applied force? What's the phrase? Constant what? Okay, and I was mean. I actually did that on purpose. I split it up onto 2 lines on purpose to really force you to pay attention. But here's the key idea. Do you see in this equation, friction is going to end up equaling the apply. It's going to be winner minus loser equals 0. See the equation? See the equation? See the equation? Ready for some deja vu? See the equation for number 9? Turns out constant speed or not moving, in terms of Newton's laws, same thing's got to be occurring. Your forces must be balanced. Must be balanced. Is that all right? Can you take it the rest of the way yourself? Or I can keep going on this if you want me to. You're good? Does anybody want me to keep going on this? I can. I have an answer.
I thought that when it's moving, the friction's always less than the applied force.
Nope. When it's accelerating,
Okay.
I got to be very careful. When it's moving, it may or may not be. In fact, it could be more than the applied force if it was slowing down.
Okay.
Right? The key is if it's accelerating and increasing in acceleration, then the applied has to be bigger than friction. Constant speed, it's a tie. If it's decelerating, which is what you do, for example, when you're rollerblading and you drag your foot, oh, now the friction force is bigger than whatever applied force was pushing you forward. Although when you're rollerblading, you're coasting. There is no applied force pushing you forwards. Is that all right? Good question. Do you want me to finish this one or not? Tyra, you put it block H? Thank you. Sorry, who said yeah? Okay. Friction is what? Were you waiting for me or are you just hanging out?
No, I'm just watching.
Jake, my friend, friction is what times what? You're right. Say it. I never said mu mg. It may end up being mu mg, but don't you dare, I'm reaching, where's my gun? Don't you dare say mu mg. It is not, it is never, I have never said mu mg. It's always mu times what? The normal force. Now, it often in physics 11 will end up being mu mg. I'm telling you, in physics 12, it'll rarely end up being mu mg. It's going to be slanty, it's going to be different. So, mu times the normal force, and it looks like the applied force is just that. Jake, what's this question asking me to find? What's mu? I don't know. What's mu with you, right? It's asking me to find mu, right? How would I get the mu by itself?
Divide.
Yep. So I get this. Don't come back here. I get this. Mu equals 370 divided by the normal force. And now, my friend, here is where I say, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one is the same size as the normal force in my free body diagram there, Jake, my friend?
Oh, no, I mean mg.
Yes, now, so this is where we make that connection. But I'm really fussy on that. I mean, I won't take marks off if you do that, but you're setting yourself up to make sloppy mistakes later on when it's not mg. I'm fussy on, make the two-step connection. Friction is what times what? Mu times the normal force. That can almost barf out of you. That's going to be the same. And then you can say, all right, what is the normal force? Look. I got to go figure it out from the free body diagram. So you're going to get this. Mu equals 370 divided by mg. In this example, it's going to be 370 divided by bracket 43 times 9.8. When you crunch it, you'll get, oh boy, a very big mu of 0.878. That would be like spiked, studded tires. Cleats on a soccer field, maybe. That's a pretty high coefficient of friction. Oh, and again, quick reminder, what are the units for the coefficient of friction? None. That's another one. Common mistake, I'll say to kids, find the force of friction, and they'll find mu. Mu's not a force. Mu is the coefficient of friction, which describes what? Just how sticky two objects are compared to each other. If I said find the force of friction, friction is what times what? It'd be mu times the normal force. If this question said find the force of friction, you would go mu times the normal force. I don't know the normal force. Oh, but look. And you would go mu times mg. Although in this case, I know the force of friction has to exactly equal 370 newtons to cancel out the constant speed that Darian asked about. Is that okay, Darian? Jake, thumbs up?
Yes.
Good. Next. Yep. 23 and me. I'd love to. I like number 23. I like number 23. I like number 23. 23 is a nice question. But I'm going to change the numbers. Yoink. Can you still see? Is that big enough? Okay, back there, Vanessa? Yeah? Okay. Change. You know how I'll change the numbers? I'll put a 1 there and 8.4. There, 15.1 and 8.4. I will expect you, by the way, what was the fancy name for this little gizmo? Begins with the letter A, you remember? Okay, we call this an Atwood machine, just a physicist who popularized this little thought experiment. Again, it's garbage. It's a magic machine because the ropes have no mass, the pulley has no mass, the pulley has no friction. But it's a good way for us to wrap our brains around a many-body problem as a start. And then if you want to be more accurate in real life, you can take it further. All right. I will expect you to clue in or to be able to figure out on your own which way things are accelerating. And what I mean by that is, Vanessa, I'm going to expect you to clue in the heavier mass is the winner. I'm sorry, I have to have some common sense of physics. Which is the heavier mass? The left hand. Which is going down? The left hand. Which is going up? The right hand. Okay? I could have put the heavier mass on the right side, that's fine, but I'm telling you, that part you'll have to figure out. Okay. And now, with more than one mass, I'm going to label my forces. I could do a completely separate free body diagram, but you've had me traditionally, because I'm lazy, when there's more than one mass, they almost always give me a picture, and I just tend to label the picture. So, what are the forces acting on the 15? This, for you three, is going to be either today's or tomorrow's lesson, I believe. I think that's what you're just about to start. You guys have done lesson 4, friction, yes? You've seen the mu times the normal force thingy? Okay, oh, you missed some classes? Okay, my videos are online if you need to. So this is, did you have physics today?
We did it.
Okay, and that was friction or? Okay, so you started, okay. So, this is how I handle these. Let's start out with the heavier one. What are the forces acting? I've told my students, I traditionally label the masses from left to right, so all of us will call the first one on the left mass 1, the second one mass 2, just so our diagrams all look the same. It's not a rule, it's just I got tired of always telling kids, let's start out with this one. So we're going to call this mass 1. What are the forces on mass 1? Get the obvious one. And I would call it M1G. I'd be really fussy because there's more than one mass. Yes? Tension. Now, this is the other reason this is not a free body diagram is I have not been careful with my arrow lengths at all. I've only been fussy with my directions. What are the forces acting on mass 2? Get the obvious one. M2G. What else? Tension. Okay? We said this. The strategy to find tension is going to be, first of all, to find the acceleration and then use that to find the tension. To find the acceleration, we look at both masses. To find the tension, we look at one of the masses. Doesn't matter which one, although usually one will be easy. Okay? So they want me to find tension. They didn't tell me acceleration. I'm going to have to write an equation that includes both masses, which means my equation is going to be winner minus loser plus winner minus loser plus winner minus loser plus winner minus equals the mass of both times A. That's going to be the key difference. Who's winning? I'm going to say that again without the cough. Who's winning? The 15 is not a force. What force from my labeled diagram there is winning? I have 2 M's. What force? Okay, I got to be fussy, and I'm doing that on purpose, okay? So scene 1, act 1, take 2, and action. Who's winning? M1G, you say with authority. Now, you've committed us now. Anything that ends up pointing that way when it gets to that side is going to be winner plus. Anything that ends up pointing upwards on the left side is going to be loser minus. My equation is going to be then I run into tension. Winner or loser? Loser. I run into tension again, which you might think is also a loser because it's pointing up, but when you follow it all the way around, what is it really? Winner. I run into M2G, which you might think is a winner because it's pointing down, but when you follow it around, and this goes, I think Anthony was asking me earlier today, Anthony, do you notice on the left-hand side I have more than one mass? You know what I better have on the right-hand side? More than one mass. That's why I have to go the mass of both of them times A. My students, what's this? Losing tension. I love these questions because you always lose tension. How relaxing is that? It's a joke, Rachel. Zing! Okay, fine. They've had me before. You're the rookie, so they know that. Look for the dumb humor. Tension cancels. I will almost always still write that just because also it reminds me I haven't missed any forces. Goes right back to my why I'll never take the shortcut of saying, oh, friction is mu mg. Only this year, only most of the time. In fact, later on this year, I'll show you a couple words not. So I have this. M1G minus M2G. You know what? I said I wanted to find the acceleration. So Vanessa, how would I get the A by itself from this line here? Can I do that on the next line? Is that okay? This particular set of masses is going to accelerate at 15.1 times 9.8 minus 8.4 times 9.8, all divided by 15.1 plus 8.4. It is worth practicing typing these into your calculator. The number of times, Kylie, that I'll see all the right numbers written for Atwood machines and then the wrong answer drives me crazy because it means the kid was too lazy. Heck, I'll even use the word too dumb to bother practicing during class time. They just assumed, oh, I'll figure out how to type this in, and they're throwing away marks. So it's well worth practicing typing that in to see if you get an answer of, do you get 2.7940, 2.79? That is the correct acceleration. It's not what they asked me to find. It's an intermediary step. In fact, I'll be honest, I think on the test, part A says find the acceleration, part B says find the tension. So I kind of walk you through the intermediary step. What did I say, 2.79? And I'll use the answer button on my calculator because it's really 2.7940425553, blah, 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 blah. What does this question want me to find? To find tension, I need to go look at one mass. Which mass? Doesn't matter. Although one is going to be easier than the other. Look closely at my labeled diagram. In which one is tension a winner, pointing in the winning direction? Mass 1 or mass 2? I'm going to write an equation for that. You could do mass 1. It's perfectly acceptable. You get the same answer. So in your mind, cover that up. There may be shortcuts, but I choose to eschew the shortcuts because I'm not convinced that they always work this year. Okay. Who's winning looking at mass 2? Who's losing? Is there more? Thank you. Because there's more than one mg. I got to make sure, right? The equation for mass 2 would be this. And did I say equation for mass 2? I did. Then it equals not the mass of both. It equals m2a. How would I get tension by itself?
Add the
Now, why does this work? The reason this works is I just figured out A in part A, no pun intended. So now it's plug and chug. It's going to be mass 2, which was 8.4 times, I'll write 2.79, but of course I'll use the answer button on my calculator, plus mass 2, which was 8.4 times 9.8. You could use mass 1, you'll get a different equation. If you used mass 1, you'd have m1g minus tension equals m1a. You'd have to do a bit more work to get tension by itself is all. It's going to be 8.4 times answer plus 8.4 times 9.8. It's going to be 106 newtons if I go to 3 sig figs. So you can definitely, and I suspect with Mr. Kamosi's test as well, you can expect an Atwood machine question on the test, on the written. Probably one on the multiple choice too, but definitely on the written. Next. Any others? Number 4? Oh, 24. I was going to swear I just did number 4 a little while. Okay. 24 is, oh, that's, oh, the nasty? Okay. Physics 12, but you know what? If you're a good Physics 11 student, barely Physics 12. So this is good practice anyways. Do you see more than one mass? So I'll label the forces because there's more than one mass. Who was that? Okay, she had to go. Okay. And it wants us to find what? Mu. I don't know what's mu with you, right? Okay. And again, in my traditional, first of all, I'm going to change the numbers a little bit. Instead of 30 and 10, I'll make it 25 and 8. Okay? Now it's a whole new question, which means the answer is going to, oh, I didn't copy the answer. Good. I'll call this big one mass 1 and mass 2 in our traditional. All right, let's label the forces. What are the forces acting on mass 1? Get the obvious one. I totally agree. Is there more than one mass? So I better call this M1G. What else? And I'll call it normal force number 1 to remind myself that it goes with mass number 1. What else? Nope. It's a rope. We don't call that applied. When it's a rope, we call that tension. What else? Which way? Gotta be. Those are the 4 forces acting on mass 1. What are the forces acting on mass 2? Get the obvious one. M2G. What else? Normal force? Nope. It's hanging in midair. Who's winning? Actually, it's a trick question. It's a tie. But if this was going to accelerate in any direction, which way would it accelerate? Could it possibly be accelerating to the left? To the left? Really? A mass can somehow pull another mass up a cliff with no outside energy? So it's moving to the right or nothing. So here's what I'm going to do. I'm going to let this here be winner. Anything that ends up pointing down and right is going to be winner plus. Anything that ends up pointing up, when it gets to the right-hand side, is going to be loser minus. So what's my equation? Well, it's going to start out with this. And now I'm going to walk along the rope. The first thing I run into is this tension right here, winner or loser. I just let that be down be winner, right? What about this tension? Follow it, follow it, follow it. It ends up pointing down, so it's a winner plus. This is where we've been stopping, but look, I have another force that's in the same direction as the rope. Vertically, these cancel, but there is one more horizontal force on the same direction as the rope. What? Follow it, follow it, follow it, follow it, follow it, follow it. Winner or loser when it gets to this side. You're telling me that when it gets to this side, it's going to point down? Which way is it pointing right now? To the? Follow it, follow it, follow it, follow it, follow it. Would it not be pointing up? Do you understand? Yes? Yeah? Up, yeah? Loser, the force, not you. Yes? Be minus. That equals, did I take forces from more than one mass? Did I write forces from more than one mass? Yes? Then it better be the mass of both times A. Is that okay, Shaq? You know what you need? You need to lose some tension because you're looking a little tense. So far, so good? Let's keep going. This is going to be M2G minus friction equals right? Right? Friction is what times what? That's good because they want me to find mu. I better have a mu show up, and it hadn't yet. So you said this is going to be M2G minus mu times the normal force equals yes? I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. Which one? Because there's two on that diagram. See the normal force? M1. Yes? Shouldn't be guessing here. Do these not have to be the same, right? There is no normal force here. Right, 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 right? So I can say this. Drop that down. Mu so far, so good, kiddo? What am I trying to find? Well, I don't know. What's mu with you? Oh, what's immediately in front of the mu? No, immediately in front, even before that. No, right in front of the mu. A negative. I don't like that. You know what I'm going to do? I mean, this is where to get the mu by itself, you got several options. But what I'm going to do to get rid of the negative, I'm going to plus that there. At the same time, I'm going to minus this whole thing here. I'm going to get this. M2G minus bracket M1 plus M2A equals, I'm getting there, equals mu M1G. This is the generic would handle anything equation, but this question is specific. It says, what does that mean? Without moving, what does that mean? I have no idea what you're saying, but I think you're right. Say it with some authority, like you know what you're doing. No acceleration. That means that this here is zero. In fact, I probably could have canceled out that earlier, but what's 0 times 10? What's 0 times a million? What's 0 times a bracket? Still. Okay? But had this question actually given me an acceleration, you can see I could have handled that too. I would have put the two masses in the brackets and I would have written the acceleration there. Meanwhile, I end up with this, my friend. Divide what? Mu is going to be M2G divided by M1G. Now, something kind of strange happens here. Do you notice? And what does that mean? It turns out for this particular situation where it's not moving, G, the 9.8, is irrelevant. What that means is if you had Star Trek technology and you beamed this to the moon where G is different, it still wouldn't slide. or if you beamed this to Mars, where G is still different, it still wouldn't slide. It would still be in equilibrium. It would still be balanced. Or if you could somehow beam this to the surface of the sun, avoiding all the burning up stuff, if you could somehow magically prevent it from burning up, where the surface of the sun has a really huge G, you know what? It would still be in balance, which this is the first time I think this has happened before, but you've discovered something universal. Anywhere in the universe, that particular setup, with whatever that mu works out to with the numbers that I made up, what did I say, 25 and 8? I should be able to do that in my head. 25 divided by 2 is 12.5, divided by 2 is 6.75, divided by 2 is 3. Oh boy, this is way too big, Mr. Dueck. This is what happens when I make up numbers. Yeah, that's a really, really big mu. That's like glue or something. I should have made the mass bigger, but oh well. Sorry, bad numbers. What was the actual answer for that one? 0.33. 0.33? Oh, I put, yeah. It's M2 is 8, Mr. Dueck. How about looking at the diagram? It's 8 over 25. Oh, that makes way more sense. That I can do in my head, I think, as well. Dividing by 25 is the same as timesing by 4 divided by 0.32? Yeah. I grew up without a calculator. Anyway, okay, fine. Is that okay, Shaq? Am I gonna, folks, I want to be clear. Am I gonna ask you one that tricky on the test?
No.
No. Would I expect you all to have followed that explanation? Because I think that's good, fundamental free body, winner minus loser, getting by itself. Oh, constant because without moving, acceleration cancel. I would expect you to follow my explanation. Physics 12, I would consider this a C plus, maybe B minus level Physics 12 question. Okay. Without friction, it would be easy. With friction, brings it to a C plus B minus level. Yep. Gesundheit. Any others? Yep.
Is that like number 25?
Oh, is that like number 25? I don't know.
The second one with friction?
Oh, tug-of-war. I think I'm going to visualize two masses, so probably a free body diagram, and let's change some of the numbers here. So what I did is I got a little sneaky. I made you lighter with good shoes. I made your friend heavier with socks. Who's going to win? Because I think the mass will play a role, but the socks will also play a role. I think what we can kind of visualize is this. There's me. There's my friend. I'm going to do a free body diagram. And are they connected with a rope?
Yes.
Then you know what? Let's connect him with a rope because I think tension's going to appear in this equation. I think this is a disguised Atwood machine. Without a pulley, but I think it's going to be kind of similar. What are the forces acting on me? Get the obvious one. I'll call that M1G. And normal force number 1, because I know I'm not sinking into the ground or flying into the air. What else?
Friction.
Friction. What else? Tension. And I think that's it. You would say, Mr. Dueck, wait a minute, wait a minute, wait a minute. Aren't I pulling? You're the one creating the friction force. But on here, it's appearing as friction. You're creating friction force by pushing forwards with your feet to get friction to go backwards. By the way, think about a tug-of-war. In a tug-of-war, you actually push forwards with your feet. You pull backwards with your hands. You're trying to generate a bit of a fulcrum, but that's how you're getting friction to go backwards, okay? So you might say, I should have an applied force. I think it's there. It's friction. That's what you're generating. You're creating it. What about on your, oh, and you know what? I'll call that friction force number 1 because I have a feeling my friend also has a friction force. In fact, I think the free body diagram for my friend is going to look the same. It's going to be M2G, friction normal force number 2, friction force number 2 and tension to the left.
Hi, Tony.
Okay. Who's winning? I don't know. So I'm going to guess. I'll know I guessed wrong if when I solve for acceleration, I get a negative answer, then I guessed wrong. So, you know what? Let's guess wrong on purpose, because the answer said that you're, oh, first of all, you know what? Let's change the numbers. Let's make me a little lighter. Let's make my friend, though, a little slipperier. Okay? Now I don't know what the correct answer is. I'm going to guess that my friend wins just because the way I've drawn it, friction 2 is pointing towards the right, and in so many of our questions, stuff moved to the right. Maybe as a habit, I said, well, I'll assume that to the right is winning. So let's decide. If I get a negative answer, I've guessed wrong, but it'll be a really easy fix. I'll just change every winner to a loser, every loser to a winner, and I think I'll be okay. Who's winning? Let's pretend friction force number 2. Anything that ends up pointing to the right is going to be a winner. So now walk down the rope. And plus tension minus friction force number 1. That equals the mass of both of us times A. Why the mass of both of us? Because we used forces from more than one mass. Turns out, although you might think during a tug of war there's lots of tension, turns out in terms of the physics, tension cancels. Hey Jake, friction is what times what? Good. So friction force number 2 is going to be mu normal force number 2 mu. Oh, you know what? They each have different mu's, don't they? So I'll call this mu 2. I'll call this mu 1. Friction force, normal force number 2, that equals, I don't know normal force number 2. Oh, but look. I know another force that's the same size as normal force number 2, m2g. I don't know normal force number 1. Oh, but look. I know another force the same size as normal force number 1, m1g. So I think my next line, Olivia, I can say mu 2 m2g minus mu 1 m1g equals, and you know what, Olivia, let's get the A by itself on this line if that's okay. I have no idea whether I've guessed right because I made the numbers pretty close. What did I say mu 2 was? I changed it to 0.3. I think that might have tipped it over the edge, and I think I might have guessed wrong, but we'll find out. 85 still. 9.8. Take away 0.5. What did I say? 55. But I made myself a little lighter. Times 9.8. All divided by 85 plus 55. Bracket 0.3 times 85 times 9.8 minus 0.5 times 55 times 9.8 divided by bracket 85 plus 55. Ha! I guessed wrong. First of all, barely wrong, because that's really close to 0. You get negative 0.14? Or am I wrong? Oh, okay. Now, I guessed wrong. How do I know? But look how easy a fix it is. Look up. Just watch. I guess that's a loser. That's a winner. That's a loser. That's a winner. The tensions still cancel. Loser, winner. Loser, winner. Loser, winner. Hey. Put a negative in front of there. Make that a positive. It really is an easy fix if you guess wrong. And I get the same magnitude of 0.14, but since I got a positive answer, I can be assured, the correct direction was I won. Barely. I'm accelerating in the winning direction to the left, at 0.14 meters per second squared. Understand, what does that mean? That means if I have to drag him 2 meters in 1 second, I won't have gone very far. You could actually calculate how long it would take me to win this tug of war. I think it would be fairly lengthy. Yes?
I did this in a simpler way.
Oh.
Yeah, what'd you do?
I just found the force of friction using mu mg. So whichever one had the most
Yep.
friction.
Yep. That what it comes down to, the comparison ends up being who's bigger, and in fact, it's the difference between the two that generates the acceleration. Yeah, there's all sorts of shortcuts. What I'm big on, Carly, is rather than memorizing a specific shortcut that works for the specific situation, I prefer not to memorize crap that I don't need to put in my brain. If I can derive it with a quick free body diagram, because these take me 1 second, and also the nerd within me kind of finds them fun. This isn't like coloring or anything, but it's kind of drawing, sorta, kinda. So especially, you're probably taking Physics 12, we'll try and come up with a generic, oh, whatever you throw at me, I can make a diagram that fits, and I may notice a shortcut along the way. As an example, there's a bunch of shortcuts. There is a bunch of shortcuts with Atwood machines, a bunch, and they will always work. I just don't have room to memorize them. They're good. They're kind of time savers. I've got, you know what, there's other time savers in Physics 12 that I'm going to put in my brain and store there. Question back there.
Is there going to be a question
Like this?
Maybe.
Yes and no. I would have no problem if I gave you a diagram, specifically. Well, see, it's almost the same as this question. In this question, it's asking without moving. Let me show you the same question as number 25. Ready? The same question as number 25 is number 23. Because use your imagination. Could I not draw these like this and have gravity going that way and gravity going that way? Only in number 25, it's not gravity going that way, it's friction going that way and that way. But oh, once again, tension still cancels. It's exactly the same physics. It's just the pulley takes gravity and flips it so it has them both pointing down. That's all a pulley does. A pulley allows you to turn a force vector 90 degrees or 180 degrees, like in this picture here. This turns the force vector 180 degrees. This turns the force vector 90 degrees. That's all a pulley does. Having said that, that's hugely useful when it comes to industry and machines and things like that, but that's all it does. So, in answer to your question, indirectly, absolutely the Atwood machine's going to be on there, and I would argue that's an Atwood machine in disguise, but are you asking, will I throw on that? It'd be a cool bonus question or something like that, but I don't think that I would throw that on there. Physics 12? Yeah, but that would even be a little tougher than the one Shaq asked me. That would probably be a full B level question. Also, to me, it's kind of interesting. Hey, Tug-of-war, good physics in Tug-of-war. Really good physics in Tug-of-war. Or sometimes bad physics if people don't have a good understanding of physics. Put your pencils down, look up. Pause for a moment.